Soil development also relies on transformations of materials that are present in an ecosystem, whether they're originally or added exogenously. The authors state that within the soil, materials are transformed through an interaction of physical, chemical, and biological processes. And here we're going to cover that trio of physical, chemical, and biological processes that are associated with the transformation of materials. For example, organic matter is transformed by decomposition into soil organic matter. So when plants produce organic matter, microbes and other organisms decompose that and transform it into new compounds that weren't there originally. We also can have physicochemical interactions with soil minerals. And essentially this happens on the soil mineral surface. So if you have a mineral, there's interactions between organic matter and the soil mineral surface that serve to facilitate some of those transformations. Now there's also weathering that we talked about. And within weathering, we have physical weathering. And physical weathering is a transformation of materials that occurs, which is the fragmentation of parent material without chemical change. So when we talk about physical weathering, it's a transformation that doesn't involve chemical change. It's basically large chunks getting broken up into smaller chunks. Now in contrast, chemical weathering is a situation where you have parent material, rock materials, that react with acidic or oxidizing substances. And this changes the chemical nature of those materials and is part of the soil development process. So for example, we'll have primary minerals within an ecosystem, and these primary minerals are unmodified minerals present in the rock or unconsolidated parent material. So whether it's a loess soil or you have bedrock that you're starting to chemically weather, that within there are minerals that have been unmodified, and we think of these as primary minerals. In contrast, we also have secondary minerals which have been chemically transformed. And these secondary minerals are generally thought of as insoluble reaction products of weathering. So it's important to realize that these secondary minerals are relatively insoluble, and the soluble materials are something else. They're generally lost from the system or taken up by plants, and they're reaction products. So those secondary minerals occur when you have primary minerals that undergo chemical reactions but stay in the system as insoluble products. When you take a look at a soil profile, that the older that soil is, the more accumulation and the more transformation that you have, and you can get relatively large profiles of exclusively secondary minerals. So this is a tropical soil. Again, it's a cut bank or a road cut that just shows how much processing there is. It's not just at the soil surface, but you have production of secondary minerals all throughout that soil profile. Now, one of the main reactants that are involved in taking primary and turning them into secondary minerals is really the production of acid. And one of the most important acids is carbonic acid. And we get carbonic acid when CO2 is dissolved in soil, water. So when you have water and you add CO2 to it, that you get carbonic acid. And that produces the acids, the protons that come off of this, that then react and start to transform those minerals. Now, the concentration of CO2 that we get in the soil is a lot higher than what we get in the atmosphere. It can be anywhere up to 50,000 parts per million. So 5% of the air in the soil is carbon dioxide, instead of roughly 400 parts per million that we now have in the atmosphere above it. And that's a consequence of all the biological activity that occurs in soils. So CO2 builds up in the soil, and you get large concentrations of carbonic acid that have the purpose of chemically weathering minerals. Most of that Weathering occurs in the rhizosphere, not only because CO2 concentrations are higher in the rhizosphere than other places, but in addition, the plant roots themselves exude a lot of acids for a couple of different reasons, and these organic acids also further promote weathering. Now, if we take briefly just a look at some of the chemical weathering, this is an example that they have in the book of one of the more common weathering processes. So on the left in this equation, we have this mineral, which is potassium feldspar. And I have a picture of it here, a photograph of what it looks like. And then on the right, we've got a whole series of products that include kaolinite. And you can see what happens is that you have potassium feldspar, which is a common mineral, and then we have carbonic acid and some water. Protons are produced off of that carbonic acid. And what it does is that it essentially displaces in part the potassium from the feldspar, which then is made soluble, and then also some silicates, and transforms potassium feldspar into kaolinite. This silica is soluble, the potassium is soluble, and often these end up leaving the ecosystem or the soils, and all that's left is kaolinite. So when we think about the types of soils that we have and some of the reactions, the transformations that occur, it's also important to think about what parent material that we have, because parent materials are going to differ in the original mineral composition. So for example, sedimentary rocks tend to be formed from the materials that have left ecosystems, those soluble components, and they tend to be a lot more basic than soils that are coming off of igneous rocks. And so the weathering patterns are going to be different. Now, there are also differences among elements in their susceptibility to weathering, and also the differences in solubility. And there's a relatively typical sequence that we see in the pattern by which anions and cations leave the ecosystem. So this here shows the general pattern where some of the first ions to leave an ecosystem are going to be chloride, and chloride doesn't react with a lot of things and it's pretty easily lost. And then after that, it's typically sulfate, sodium, and then calcium that are lost. And by the time we're over here, after all of these are lost from the ecosystem, only then do you start to lose your irons and your aluminums, for example. The secondary minerals formed in weathering reactions play critical roles in soils and ecosystem processes. Now, it's important to state that not all secondary minerals are equal. They have very different properties and function differently within the soils. As an example, we'll think about some of the different clays that are out there. Now, clays are defined based on particle size. We'll talk about that later. But the clays are often the secondary minerals in a soil, and they really do differ in their properties. And we're going to cover the basics about how clays differ. These are two examples of two different minerals. On the left, we have montmorillonite, here in a quartz form. And on the right, we have kaolinite, which we had talked about before. Montmorillonite is a primary mineral. It also can undergo physical weathering to form clays, relatively small particles. And the kaolinite here, too, is a secondary mineral that also is considered a clay. Insoluble products of chemical weathering are often these fine clay particles, and they consist of hydrated silicates of aluminum, iron, and magnesium arranged in layers. We're going to talk about some of the basic patterns among clays and the different properties that they then provide soils. So again, when we think about these clay particles, we're going to start to think about these hydrated silicates and then aluminum, iron, and magnesium that are associated with the clays, and then their layer structure or their sheet structure. So this is figure 3.9, and this is an important one to study because it shows you some of the major differences among the different clays. Clays are, again, the fine particles that you find in the soil, the finest particles, but not all clays are built the same. And the differences that we see in their molecular structure really determine important component of the ecosystem and how that soil functions. So this diagram shows very simple clay layers. At the top, we have clays that are formed from tetrahedral sheets. So each one of these is an oxygen, and then in the middle of that is a silicon. And at the bottom, we have something different. This is a different arrangement that forms a different type of clay. And this right here is an octahedral sheet. And you could see that the pattern of arrangement of oxygens, and often what we have at the center of that unit, are really different. Now, where this becomes important and what is called cation exchange capacity. And what that simply means is that cations, which are things like calcium, which have a positive charge, can be exchanged from the surface of minerals. So this might be a clay that has a negative charge on it, and then cations like calcium become attracted to that negatively charged clay. And different clays have different abilities or capacities to exchange calcium and other cations. And that depends on their molecular structure as well as their charge. Now, what the authors emphasize is that cation exchange capacity differs among the different clays and changes over time as those clays are weathered. So after a small amount of weathering, on the x-axis we have basically how much weathering there's been of primary into secondary minerals. And then this is the amount of charge that you get on clays. And don't worry about the units here. You can think of this as a relative scale for now. So initially, you have what are called 2-to-1 clays. And these 2-to-1 clays are the clays that had this tetrahedral form. And the 1-to-1 clays were the octahedral clays. And the differences between those is how many cations can bind to the clays. So when you have these 2-to-1 clays, like the montmorillonite that I showed, those are ones that have a lot of cation exchange capacity, a lot of ability to hold on to cations. And then as that weathering occurs, you get mostly 1-to-1 clays. And these have a lot less ability to hold on to cations, which means if cations are added to the system, it's a lot more likely that they're going to be lost. And as that weathering progresses, you get to the point where, on average, your cation exchange capacity is very low, which means it's a lot more likely that you're going to lose cations from the system. And you even get to the point where you start to develop anion exchange capacity. So those surfaces tend to have a negative charge, giving you a cation exchange capacity. But over time, you even get to the point where you can develop anion exchange capacity, which means those clays are positively charged. They have relatively little ability to exchange cations and instead start to hold on to anions. And in general, anions, things like chlorides, are a lot less useful to plants than cations are. So thinking about cation exchange capacity, that's contrasted with anion exchange capacity, which is relatively rare in soils, but it's almost a terminal product of the weathering sequence. Highly weathered minerals dominated by octahedral sheets, these 1-to-1 clays, strongly bind anions like phosphate. And so by the time you're getting to the point where you've weathered soils and you get into the octahedral sheets, they're going to hold on to something like phosphate very strong. And as a consequence, it's not available to plants or other organisms that could need it. Now, lastly, the authors also want to emphasize that secondary minerals that form in soils can either be crystalline and therefore have a relatively regular structure, but also they can get to the point where they're amorphous with no regular arrangement of atoms. And so, although we talk about the secondary minerals as having a crystalline structure and having a relatively well-defined structure, often they end up being relatively amorphous with just a non-regular arrangement of atoms.